thank you very much, Anka Maria, and thank you to the organizer of this seminar for the invitation. So I have many slides, but don't worry, many pictures. And I know that following a seminar through internet by a Zoom is not the best place if you are too technical. So I will not be very technical, right? For technical details, I will refer you to my papers. I will more insist on the result and the applications. Okay, so this is a joint work with at least two former PhD students, Mathilde Boissier, who defended recently in December, and Per Geoffroy Donders, another PhD student who defended 3 years ago. And they were co-advised with Olivier Pons, who is a professor at the University of Nice, and Christophe Tournier, who is not a mathematician at all, he is a specialist of additive manufacturing machines. You will see his influence in the last part of the talk. Good. So I will first make a brief introduction to tell you a few things about additive manufacturing if you don't know anything about it, right? Then I will briefly, very briefly, review shape and topology optimization. And then I will study two different problems in topology optimization, which recently emerged because of additive manufacturing. First, the question of optimization of lattice structures. I will explain what it is. And then a combined optimization of optimal shapes, but also the laser paths that build those shapes in additive manufacturing, right? And then just one slide of conclusion. And so this, what I like in this field is that it's a very hot topic. It's a brand new idea of doing building shapes by additive manufacturing, and there is a lot of problems, and so a lot of research to do here. And you've seen the logo of a project which is called the Sophia project, which still is going on, a project in France with some people from industry. Michelin, the tire company, who has a joint venture which is called AddUp, who is building those kind of machines. Good. So some slides about additive manufacturing. So the idea of additive manufacturing is to build a structure layer by layer. You see on the left here, you have some kind of a 3D structure, and then you slice it and you will build one layer after the other, right? And what is remarkable with this process, I will explain a little bit more in detail, is that you can build structure with very complex topology. Imagine that if you had to build such a structure with traditional techniques like molding, you have a mold, you pour liquid metal, and then you remove the mold. I mean, how can you guess how to devise a mold for such a structure with so many holes? I mean, you will break the mold at some point. So it's almost impossible to build this by traditional techniques. The same for this bracket. That's a picture that you can find on internet. That's a classical test case for topology optimization and additive manufacturing. Again, you see that something which was forged or mold is now with a much more complex topology, and it is built by additive manufacturing. Good. So here, okay, one thing is I'm focusing on metallic additive manufacturing. You know that you could do things in polymers or ceramics. I'm focusing only on metallic additive manufacturing, and more precisely on so-called powder bed technique. So here is a machine where you see you have two platforms, one going up, one going down. The one that going down is where you build your structure. You have a layer of powder, and then you have a laser that goes. I will show you some movies of that, and it will bring energy and melt the metallic powder to build the structure. Once you have built one layer, this building platform will go down one layer, and then this one will increase, and you have a roller or that will or rake that will bring a new layer of powder on this platform where you actually build your structure. Good. So you see here, I will show you a movie. The light gray is a powder, dark gray is metallic, and you see the laser which is melting the powder to make it solid. And once you have finished, you just remove the powder and you discover the structures that you have built. So so my colleague Christophe Tournier has a machine of this type in his lab. So that's the machine. And here I have a small movie. So I'll try to to show you the movie to explain maybe how it works. So I'm changing the screen that I'm sharing. Maybe I'll share the entire desktop for a couple of minutes. Where is a movie? Here. Good. Can you see my screen? And now I'm starting the movie. So you see that one layer here, and you see the laser. So it's not real speed. Huh? It's you see jumps in some sense because you don't have a 24 image per second. But you see it's building, and here you see the raker has come and built a new layer. So that's the way it goes more or less. Okay, good. Coming back to the slides, maybe I will have a larger slide. Ooh. Oh. Yeah, sorry. Good. So what can be achieved? You can build. I will come back to the full screen, but since I have other movies, that's better maybe to stay like this. So what can you build with additive manufacturing? So no topological constraint, and you can build very complicated structures. And in particular, what are so-called lattice material? They are porous materials. So you see here a kind of a picture. It's a kind of a fractal pyramid. Or this one, made with some kind of square lattice. So with many small holes, and I will come back to this. And you can also build functionally graded materials. So that means that the microstructure can change locally. So you can grade the porosity of those materials. So here are a few examples coming from my colleague Christophe Tournier. Again, lattice structures. This one are so-called comb-shaped structure. They are a very classical test case to see if you can build them correctly. I'm not going to discuss them a lot. Other picture of lattice structure. And so, I will come back to the issue of shape and topology optimization, but there is a lot of potential in structure which are very complicated with many small holes because they are supposed in some sense to be more optimal than standard shapes. Good. So there are many new problems, and I will discuss only the two first ones, which are in blue. The first one is, okay, how do you optimize those lattice structure? And that's a joint work with Per Geoffroy Anders and Olivier Pons. The second problem that I will discuss at the end of the talk is a simultaneous optimization of the laser path. You've seen this laser, which on my movie was only going in straight line, but you could imagine a much more complicated path, typically to minimize energy or to minimize the time of building. And so this is something recent that I did with Mathilde Boissier and Christophe Tournier. Then, of course, there are other issues like standard shape optimization, but taking into account the fact that you are going to build your structure with additive manufacturing. And actually, there are some constraints. If you don't have any topological constraint, you have constraint because, of course, you can imagine that the laser brings a lot of energy to melt the powder. And so if it brings a lot of energy, then you have so-called thermal residual stresses, which mean that there may be some defect in your structure that you try to avoid. So maybe you should take that into account when you design your structure before you build it. Then there is a question of optimization of supports or the simultaneous optimization of the shape on the graded materials, the anisotropy of the porous material. I'm not going to discuss the three last issues, but just to show you that there are, and probably there are other problems that could be addressed, and I'm just discussing the two first ones here. Okay, so that's all I want to say about additive manufacturing, and then I just want to tell you a few words about shape and topology optimization, just to motivate why we are so much interested in lattice material. So a problem of shape optimization is how you optimize the shape that I will call capital omega, maybe with some constraints. So you want to minimize an objective function for some shapes in a set of admissible shapes, that is including some constraint. And the difficulty of the business is that the objective function is not computed directly in terms of omega, but also in terms of a U index omega, that is a solution of a PDE, which is posed in the domain omega. So you see that the dependence on omega is very implicit through this solution of a PDE posed in omega. So to be more specific, Here we are interested in the model of linearized elasticity. So that means that in the structure omega, we compute the so-called elastic displacement U, which is a vector valued function, right? E of U is a symmetrized gradient, the so-called strain tensor. A is Hooke's law of some isotropic material characterized by Lamé coefficient. And so A times E of U is a stress tensor. The divergence of the stress tensor is equal to 0. I neglect body forces just for simplicity. The structure is fixed, U equal to 0 on some part of the boundary. There is some surface law that I call G on some other part, Neumann, of the boundary. And then I have a free boundary. And the typical objective function is the so-called compliance, which is the work done by the load. And if you minimize the compliance, you more or less maximize the rigidity of your structure. So I have a small picture to explain. This is a picture of a so-called cantilever. That's a classical test problem. You see that it is fixed on gamma D. This is on the left. On gamma N here on the right, you have some vertical load. On the dotted line, gamma is a free boundary, no traction, and that's the part that I want to optimize. So a typical set of admissible shape is to say that any shape omega must belong to some big domain, capital D. Gamma D and gamma N are fixed. They are part of the boundary of omega. You cannot remove them, right? And typically I will fix the volume, because if I don't fix a volume constraint, then the bigger, the stiffer, so the optimal shape will be omega equal to the full domain capital D. Okay, so you have to prescribe a volume fraction if you want to have a balance between rigidity and lightness. Okay, so the important thing is that gamma D and gamma N are fixed. It's only the dashed part which is optimized here. So problem is that it's known since a very long time that there exists no optimal shapes if I do not add any regularity constraint typically. And there were some counterexamples by François Murat back in the 70s, and there were some numerical evidence, and I will show you some numerical evidence again, that if you refine the mesh, you have no convergence of your design. And actually the main obstacle is the so-called topology, okay? So I will explain it a little bit with some movies, and that's a motivation to study lattice. Of course, you can obtain existence of solution if you have some further constraint, regularity, topological constraint, perimeter constraints. Okay, I'm not going to discuss that, just to tell you that if you don't have further constraint, in general, you don't have existence of optimal shape. So let me show you how it shows up in numerical computation. So that's my cantilever problem, right? And on the left, I have my initialization with 4 holes, right? And so I'm going to optimize to minimize the compliance. And the optimal design that I obtain is the one on the right. So you see that it has changed a lot. I mean, the free boundary has moved. In particular, the more or less circular initial holes became rectangular holes, right? And instead of holes, you really see now more kind of a pair of bars like this. And it converged nicely. So you see, I guess, my movie here. You see that the mesh is updated at each iteration. What you see is every iteration is one shape with some optimization algorithm, a gradient algorithm. And so, okay, the topology is fixed. You get a solution which is better than the previous one, than the initial one, but with 4 holes, right? So let me come back to the slides. Where are my slides? No, that's not here. Yeah, here. So this was an initialization with 4 holes. If you take another initialization with a different number of holes, let's say 7, you get a different optimal structure, right? Here is a movie for the 7 holes initialization. Okay, and what is really interesting here is look at the bar, the vertical bar on the left. It's becoming thinner and thinner. And actually, the algorithm is going to stop not at a local optimum, but it's going to stop because the meshing algorithm, you see the mesh is changing. So I need to remesh at every iteration. And the meshing algorithm breaks down because the bar is too thin. So, you want to break the bar, you want to change the topology, but this was not in the algorithm, and this was not also in the meshing algorithm. I mean, there are very few meshing algorithms where you can change the topology when you change the mesh automatically. And so, clearly, you have many local optimas due to topology, but even you want to sometimes to change the topology, and the algorithm is not done for that. All right, where is it? Tech shop. Good. So topology optimization is important, and there are various methods to do topology optimization. The oldest one is the so-called homogenization method. There are many reference books because it goes back to the end of the 70s or 80s. Then there was something which was much simplified, but inspired by homogenization, which is called SIMP, for solid isotropic material with penalization. It's a kind of very simplified method of homogenization where you only keep the idea of having a density of material. And I refer to the book of Benso and Zygmunt, which is a very well-known book on this topic. You also have the method of topological gradient. And then I'm doing some advertisements. That's why I have this new logo here, because we recently released with my colleague Charles Dapogny and François Jouve, part of a chapter in this series of the Handbook of Numerical Analysis on shape and topology optimization, where we use the level set method. So, either you can buy the book, or there is a preprint that you can download for free, and that's the same. Okay, so good. So we have those different methods, and just want to show you how topology optimization works in the context of the level set method, just so that you have some ideas, right? So here, this is another problem. You see, this is in 3D. You see the boundary of the structure. It started with a half domain full of material, the lower half, and you see it converge with a different topology. So why is it this topology? That's because I have 5 points where I have Dirichlet boundary condition on the bottom side of this box here, and it's a uniform pressure load. And you see that it changed the topology very easily because of the level set method, which is done specifically to change topology, right? Okay. So another one that I like very much, which is this so-called L-beam. It's fixed on the upper side here. You have a vertical downward load over there. That's the optimal shape, but you will see how it evolves. It starts with some holes, some spherical holes. And what you see is only the exterior shape, you see. And starting from a few holes, you get a structure which is completely different in the sense that it's made of bars. And what is specific in this, test case...
Obrigado aí. Eu acho que a logística, cara, melhor deixar guardado lá na Coptec e a gente pegar esse material depois.
Okay, thank you. So what is very specific to this test case is that the structure is meshed exactly. So here I have a meshing algorithm in 3D. Let me play it again. I have a meshing algorithm in 3D, which is following the boundary of the structure, and you see that the topology changes. We started with a few holes, and then what we got in the end is many handles. So there is a change of topology, and the mesh is following this topology. Good. So enough movies. So I'm going to change and share only my slides now. This one. Good. And okay, let me come to the optimization of lattice structure. So you've seen, on movies that topology is important, and actually it turns out that the more holes you have, the better the structure. So the idea is to say, well, maybe we want to design structure with many, many, many holes, so many that you cannot compute exactly, the solution of the linearized elasticity equation in a structure which is so complicated, right? So now I have a modeling issue. How do I model lattice structure? And I make a choice. And my choice is to say, well, of course, with additive manufacturing, I can build many holes, but still, I cannot go to very, very small scales. And so I'm going to say, I have a macroscopic size, and then I have a microscopic size, which is the size of my holes. So it's going to be a 2-scale structure, but not more than 2 scale, not 3, not 4. I don't want to build laminates. For those of you who know that, I just want to build something with two scale, so the macroscopic scale and the microscopic scale. So my idea here is a picture is, you see, for example, if I have a cube or structure, you know, a structure like this, I will have holes, and you see that all holes have the same size that I call epsilon, which is a small number, but I don't have holes of size, let's say epsilon and epsilon square. It's two scale only, right? And so the one way of modeling this is to say, well, my structure is defined by some function that depends on two variables, the variable x, which is a macroscopic variable, and then a microscopic variable that I call y, in a unit cell. You see in my picture, the unit cell is a square, and this x over epsilon describes the periodic geometry inside each cell. But because of the x variable, the first variable here, you know, every unit cell may be different from one place to the other. So you see that indeed you recognize a square cell everywhere, but let's say the shape of the hole inside every square change because of this x variable, okay? And so because of additive manufacturing, you can build lattice structure, and lattice structure, you know, if epsilon is very small, you cannot make any direct computation of this problem with many small holes. So you need to use homogenization. So in some sense, it's a resurrection of the homogenization theory, which was completely killed by CMAP, but CMAP does not describe any microgeometry, while homogenization is really relying on a microscopic geometry. Okay, so here are a few references. Actually, the pioneering paper here is very old, not at all, but you know, they didn't know anything about additive manufacturing at that time. But some of the ideas were already in this paper, and then there's been some joint work with Pierre Geoffroy and Olivier Pons, and at the same time, Ole Zygmunt with his student Jeroen Groen, they had more or less very similar ideas as we did. Good. So there are many modeling issues, and in particular, you know, I said, okay, only two scale, so no sequential laminate. You need to choose a period, and I will choose a period which is a square. But if you tell me I prefer to build an hexagonal lattice, no problem. I mean, everything goes to an hexagonal lattice, but I choose for simplicity a square lattice. Then you need to choose a parametrized cell, okay, I will show you what is my choice. And then the crucial issue is really the orientation. You see, if I come back to my picture here, you see that I changed the orientation of the, you know, hole, which is like an ellipse. But that's not the type of orientation I want to talk, because if you do that, you see that, you know, whatever the size of your ellipse in every square of your mesh, of your lattice, you still have big vertical bars and big horizontal bars, you know, and they are not oriented, you know, they are fixed in the horizontal and the vertical direction. What I want to do is I want to orientate my lattice, okay? And that's very important. Okay, again, also I'm using homogenization theory. There will be no existence of optimal design. And if you choose a bad unit cell, it shows up again numerically, because a bad unit cell means that you get a very bad design in the end. Okay, so let me come to the choice of the parametrized cell, and I choose something very simple, which is a square cell with a rectangular hole. This was the original choice of Benso and Kikuchi in their 1988 paper, you know, a long time ago. And so this cell, this is a unit cell, so it's parameterized by the size of the hole. So you have two parameters, M1 and M2, right? And of course, you can rotate it. So the third parameter is the angle alpha in 2D. So I'm going to explain you in 2D, and then I will show you some example in 3D later. Okay, so the point is that with such a unit cell, you can compute homogenized properties that I call A star. They are, you know, this homogenized material built with this periodic cell is not isotropic. Even if you take M1 equal to M2, it's not isotropic, it's orthotropic at most. Okay, so A star is a bit complicated. It depends on M1, M2, and alpha. And so why do I choose this one? Because it's very close to the optimal rank 2 laminate that we know which is optimal for this problem of compliance minimization. But okay, if you choose another geometry, still we can compute the homogenized property by standard application of homogenization. Okay, now I have a three-step approach for optimization. The first thing that I have to do is to compute the homogeneous. all fine, once and for all. So you give me a unit cell, I compute the homogenized property for all values of the parameters. You know, M1 and M2 varies between 0 and 1. The angle alpha varies between 0 and 180 degrees. So you discretize them, you compute all homogenized property. No big deal. Good. Then, once you have computed this, you do a simple so-called parametric optimization. That is, you are going to optimize in your big domain, capital D, the optimal. You are going to optimize the values of M1, M2, and alpha, which may vary from place to place depending on the macroscopic variable. And that's simple because that's, you know, parametric optimization, right? Everywhere you optimize the value of M1 and M2 and alpha, let's say to minimize compliance. Good. And then the third step, that's the complicated one. That's where we, you know, bring something new, which is to reconstruct a periodic domain, which is an approximation of this A star, which was optimal in the second step. Okay, so in the second step, I've computed something which is homogenized, and now I choose a length scale epsilon, and I want to construct something which is periodic like this, which is an approximation of this homogenized design. Okay, so the smaller epsilon, the closer it will be to A star. But of course, maybe you want to choose epsilon not so small because your machine is not building very small holes. Okay, that's of course a delicate step of the approach. Okay, so here is the orientation. You know, I choose a square cell, so I have a square lattice. But now I am able to rotate. You know, I have this angle alpha that rotates every one. So when you compute, you know, after optimization of your macroscopic structure, when you compute alpha, for example, you get an orientation like this. So my orientation here is just a line segment. There is no arrow because if you orientate up or down, that's the same structure. If you remember from my rectangular cell, if you rotate up or down, that's the same. So it's arrows without the arrows, huh? In some sense. Okay, good. So now what you want to do is you want to deform this so that it's always oriented like this. So what you want to do is transform your square lattice to this, you know, curvilinear lattice, which is well oriented. Of course, in this transformation, every cell is slightly distorted, right? But the smaller the size, the smaller the distortion, right? But actually, that's the only way that you can rotate cells so that they do not leave gap between them or they overlap. You see, you must distort them if you want to align them with the optimal angle of orientation. Okay, so that's how you do that. That's the difficult part, and I'm going to explain it. Okay, so first step, pre-computing the homogenized property, it is standard. For the orientation, that's just a rotation of the Hooke's law, right? You have a fourth order tensor, which is the Hooke's law for the fixed angle alpha equal to 0. You apply a rotation tensor on the left, on the right. The rotation tensor applied to a matrix is just, you know, change of coordinate, where Q alpha is the rotation matrix of angle alpha. And then for every M1 and M2, you have homogenized property, you have explicit formula, you compute them. So for example, here you have some entries of this homogenized tensor depending on M1, which is the horizontal axis, and M2, which is the vertical axis. Okay, so you do this computation, no big deal. Good. Second step, parametric optimization for the homogenized problem. So I have a big box D that will contain my lattice, right? And in D, I assume that I have no bulk forces for simplicity. So I solve the equation of linearized elasticity, but with the coefficient coming from the homogenized material, the boundary condition, surface load G on part of gamma n, and I minimize compliance. So I minimize compliance, and now it's not a matter of shape, it's a matter of parameters, M1, M2, and alpha, right? So let me show you the result of this. That's very simple. So I choose the so-called bridge test case. So my domain, capital D, is a rectangle. I have a vertical load at the bottom side in the middle, and I have zero vertical displacement on gamma D, which is those two parts here. So what I obtain is this. So this is the density of material. You see M1 and M2 vary between 0 and 1. White means 0. So the density is 1 minus M1 times M2. So I plot the density. So you have 0 material where it is white, and you have full material where it is black. And you see that you have a lot of arrays where it is gray. So you have intermediate volume fraction. And in particular, what is interesting is to see that you have the cell orientation, which is here, which is radial. Okay. Okay. Here are the plots of M1 and M2 if you want to see what it is. But what is important is the density and the orientation. Let me zoom on the orientation. Here is the orientation. So the orientation is radial. That means that the hole is oriented to be in this direction radially, because of course, since you are pulling on the back, it makes something which is a radial, right? Good. So first remark is you see that sometimes you have jump in the direction of this arrow, because this arrow is cos alpha, sin alpha. And sometimes you have a jump from alpha to alpha plus pi. That is the direction of the arrow jump. And the point is that alpha or alpha plus pi is the same orientation of the geometry, because the geometry is something orthotropic. It's a rectangular hole. If you change it by an angle of pi, that's the same. So it does not change. So the fact that you have sometimes up and down, it's the same. Okay. So you have something which is not smooth because of that. But you have further singularities. Look here in the two upper corners, you see it's not very smooth. Why is it not very smooth? Because the density was 0. Okay, so if the density is 0, you have no material. So whatever the orientation, you don't care. So the orientation is not smooth where the material density is 0. Here and there, again, it's not very smooth. But here and there, the density of material was almost 1. It's black. So again, the orientation does not matter. If you have full material, no hole to orientate. So you have some values of the orientation, but you don't care. Okay, so the non-smoothness is really linked to void or full material, or this point here is different. This point is a real singularity. Okay, so the third step is now we want to reconstruct an optimal periodic structure that looks like this homogenized design. Okay, so a priori it's something simple. It should be only a post-processing step, but it's a bit more complicated. Okay, so the idea, which is the idea of point central Bell-C, is to, from this rotation matrix defined by this angle alpha, to deduce a map from R2 into R2. So phi is a vector of two components, phi 1, phi 2, that will distort your regular square grid into this oriented lattice that will be the one that we want to build. Okay, so the idea is, okay, if you have this map phi, when you compute the gradient of phi, this is a matrix, right? And you want it to be proportional to this rotation matrix. And so the idea is to say, okay, proportional, but the coefficient of proportionality may vary from place to place. So you want to find a map phi such that the gradient of phi is exponential r multiplied by this rotation matrix q alpha. R is a dilation factor. Okay, so why do I put an exponential here? Because I choose to normalize this coefficient to be always positive. So this coefficient is a scalar. I call it exponential r, so I'm sure it's always positive. And r is a dilation factor. That means that some place you will have very small cells, at other place larger cells. Okay, so can you find, if you give me a matrix of rotation q alpha, can you find map phi such that its gradient is equal to this? So you have, the liberty of choosing the dilation factor. And the answer is yes, but there must be a condition on alpha, which is the so-called conformality condition. So I have a lemma for that. It's a very classical lemma. Assume that alpha is a regular orientation field and that D is simply connected, then you can find phi solution of this equation if and only if alpha is harmonic. And the proof is very simple, the proof at least of the necessity, because what you do is assume that you have a solution, you take the curl of this relation, the curl of a gradient is 0, and when you compute the curl of this thing, you get another equation that tells you that the gradient of R is equal to this gradient of alpha transpose, and so you take again the curl and you get the Laplacian of alpha equal to 0. And then to go the other way around is just a little bit of further work, but you use the simply connectedness of alpha of D to reconstruct phi. Okay, so you have this condition. If you want to build a map phi that is always aligned with this rotation matrix, you need to have alpha which is harmonic. Okay, is it true that alpha is harmonic? Alpha, it turns out, is always an eigenstress direction. You know, how do you compute the optimal direction of alpha? That's a famous result due to many other authors, but the most famous one is Pauli Pedersen, who showed that you should orientate your cell in the direction of the principal eigenstress. What does that mean? You take the stress tensor, you diagonalize it, you get two eigenvectors, and then this will be the two direction of your cell. Okay, so alpha is linked to this. Is it harmonic? No, there is no reason that it is harmonic. It comes from an optimality condition. There is no reason that it is harmonic. Even worse, I showed you that alpha is not smooth at some places. So how can I compute the Laplacian if it is not smooth? So we need to regularize the angle alpha and make it harmonic. Okay, so there is a first thing, which is to regularize the orientation angle and make it harmonic. So what does that mean? That means that starting from my optimal alpha, I change it slightly. I don't explain how I do that, but that's a standard. So I slightly change it to regularize it and to make it harmonic. And so here you see it's much smoother, and I can, believe me, I can prove that it is harmonic. This orientation field here is harmonic. So what is the difference? Well, this is the picture of the difference, of the absolute difference. Where it is white, that means no difference. Where it is black, that means a lot of difference. And you see that the difference is where we have this zone of zero density or density 1, where the orientation does not matter. Okay. Good. Now that we have regularized this angle alpha, we can build the map phi. And here I show you the isolines of the two components of this map phi 1 and phi 2. So that's the iso values of phi 1, that's the iso values of phi 2. And you can recognize again this radial structure that we saw in the angle alpha of optimal orientation. And then I apply this map phi to my square lattice, and that's what I get. Okay, I've deformed my square lattice in a lattice which is well oriented as I want. And of course, you see that the importance of the dilation factor, because far away from the center, you have big cells, closer to the center, you have small cells. That's the price to pay if you want to have this orientation, which is optimal. Okay, good. And now what do we have to do? Well, you know, in every square cell here, we just put the value M1 and M2 that gives the whole. Okay, and so that's what I got here. You see, I choose different values of epsilon large or epsilon small, and in every square cell which is distorted, I put M1 and M2, so I put the rectangular hole, and that's what you see. Okay, so it's not completely finished because you see that you have very small lines. You know, maybe they are not connected to the rest of the picture. It's difficult to, you know, because the quality of the picture is not great. It's difficult to detect. So we do some cleaning, you know, removing disconnected components and things like this. And after this last cleaning, that's what we get. Okay, so you see, I've removed all the components. Okay, and I get a structure like this. So those structures are the smaller epsilon, the closer they are to the optimal homogenized tensor A star that I computed in step 2. Okay, but of course you see that I have many holes. It will be impossible. Well, not really, but in 2D that will be possible. But in 3D, imagine that you do the same in 3D. You have so many holes that it's too heavy to compute by a finite element analysis. So what I've done is I've computed the homogenized tensor, and then it's only a post-processing step, this step, right? So you can do other examples, and here is a so-called cantilever that I've already shown you. So it's fixed on the left wall. You have a vertical load at the middle of the right wall, and you minimize compliance, and you see the optimal orientation. You see here the distorted grid, okay, the distorted square grid, and you see that if you take a smaller epsilon, you have more and more bars. It looks like exactly the so-called Mitchell truss, which is known to be optimal for this cantilever case when the volume fraction is very small. Okay, that was a cantilever. So now another type of beam, the so-called L beam. I've shown you a 3D L beam. So it's fixed on the upper side. You have a vertical load at the middle of the right side, and you see a different orientation, the deformed square grid, and for different values of epsilon, the structure that you get. So you see that the main idea, which is really interesting, is that you may have a very detailed structure, but you never compute any finite element analysis in this detailed structure. You do all computation at the level of the homogenized model. Okay, how do you generalize this in 3D? So I have to choose a unit cell in 3D. And here is my choice of a unit cell in 3D. And this choice is dictated by the fact that since I'm going to build it by additive manufacturing, there is some powder and I need to remove the powder. So I don't want to have a closed hole. I want to have holes which are connected to the outside so that I can remove the powder, right? So you see that my cell is obtained by taking a cubic cell, and then I perforate it with 3 cylinders with a rectangular cross-section. So you see here that I have a cross-section which is a rectangle of size M1, M3. This cross-section is then in the direction of the axis vector E2, and in every direction, for example, here I will have M2 and M3 in the direction of E1, and so on and so forth. So I have 3 direction of channels with voids, so I can remove the powder. Okay, so again, I can compute the homogenized property for this unit cell depending on M1, M2, and M3. But of course, now I will have more angles of rotation instead of just one angle. And instead of working with angle, it's better in this case to work with a full rotation matrix. I call it omega 1, omega 2, omega 3. Omega 1, omega 2, omega 3 are the 3 vectors, of the orientation of this cubic cell. Now, there is no more conformality condition. Very unfortunately, there is a theorem by Liouville saying that there are very few conformal maps in 3D. So I cannot apply the conformality property. So what does that mean? That I cannot solve nabla phi. Phi is a map with 3 components. So nabla phi will be a 3 by 3 matrix. And I cannot say this is equal to exponential R, a single dilation factor, times omega 1, omega 2, omega 3. It is impossible, right? So what I do is I do it row by row, component by component. So for every component I of my map phi, I compute nabla phi I, a vector, equal to exponential Ri, a dilation factor in the direction I, okay, times omega I. So I have 3 dilation factors for the 3 direction. So I'm cheating here. I'm cheating because I can't do better for the moment. I'm cheating. That means that my cube will be dilated differently in different direction. So my cube will become a rectangle. So also I compute homogenized property with a cube. I'm going to use it as if they were rectangles. So I'm cheating. Okay, so there is a mistake here because I cannot, have this conformal mapping. I need to do a change of variable direction by duration, and so I transform a cube in a rectangle. All right, just to tell you how do I build this. You see, to build my cell here, what I do is I first build layers in the 3 direction. You see layers in the 3 direction. Then you do intersection. For example, intersection between those 2 type of layers give you pillars in the 3rd direction here and there. And then you do union. So you build layers, you do intersection, and then you do union, and that's the way you build it. Why do I do that? That's because the way it is coded, but also because if I show you this cell in 3D, you will see the cell on the boundary, but you will never see what happened inside. So I'm going to plot the layers from which you know how to rebuild this. Because if I show you that, you can't see anything. So here is a cantilever. So the side on the back is fixed. I have a unit load horizontally here, and you see my 3 layers, so you see the orientation, and that's, when you have those layers like this, you do intersection, union, and you get back to your structure. But here, at least you see what happened. When you do the intersection, that's what you get. You see, you can't see what inside, but you have to imagine that inside you have many holes percolating, so it's a completely porous structure, okay? Of course, for 3 different values of epsilon, refined as you go from left to right and top to bottom. Another example is a bridge test case. So remember, I have a vertical load here. It's fixed on the 2 lower edges here. And then you see again something which is like a radial structure. This is a 3D mast. electrical mass, you see a very complicated structure. Here you see a big pillar, but you have to imagine that it is full of holes inside. If you do cross section, you can see the holes, but it's hidden. Good. So that's it for lattice material. So people are full of hope on those lattice material. I'm not sure it will be completely successful for some reason that I can explain if you have questions, but okay, people are really excited about lattice material. Now let me come to another application, which is a combined optimization of the shape of the structure and of the laser path that will build the structure, okay? So I will start by simply optimizing the laser path, which is a curve in the plane. You see, we build layer by layer, so we look at one layer, and I want to optimize the path of the laser so that I can build my structure in a minimal time, okay? And then in a second step, I will do the couple optimization of the laser path, but also of the structure, so the structure will have a final use, but I want also to build it in a minimal time. So let me start with the optimization of the laser path only. So the idea, I call gamma this laser path, which is in my rectangular domain, and I want to minimize its length. So I'm going to show you a very simple model, which is a steady state model. Of course, you could imagine that you could look at a time-dependent model. It's more or less the same, except that it is a little bit more complicated. So I'm looking at a steady state problem. So you could imagine that you have your layer, your path, which is put at once, okay, and you don't see the real displacement of the laser. So you minimize, and you will have some constraint, and the constraints are on the temperature, which is produced by the laser. So I have the heat equation. So as I told you, this is a steady state heat equation. You recognize the diffusive term. Because this is in a layer, so this is a 2D problem, you have to take into account the fact that the temperature can also escape in the third direction, in the normal direction. So I have an absorption term, which is here to account for the fact that heat can escape in the third direction, but I'm doing a 2D computation. And then I have a source term. P is a power, and delta gamma is a Dirac mass along the path. You see, I have my path here, so I put a Dirac mass along this path, and I'm applying the path once at a time because this is steady state. And Neumann boundary condition on the boundary. Good. So what do you want? Why do you need to compute the temperature? You need to compute the temperature because you want to check that you melt every single point in the structure that you build. So the temperature must go above the phase temperature, the phase change temperature that I call T phi. Okay, so everywhere in the shape that you build, sigma S, which is a subset of sigma is a big rectangle, sigma S will be a subset, that's what I want to build. You need to be sure that T will be above T phi, so you're really melting. So, you have a criterion, a constraint, depending on T. So you take T phi minus T, you take the positive part, square it, integrate it on sigma S, and this must be 0. Okay, so you need to be sure that you melt sigma S. Good, but now you want to be sure that you melt sigma S only. You don't melt the outside of sigma S. So there is a maximum temperature, okay, outside from sigma S. The temperature should not be above T phi. But even in sigma S, you want a high temperature, but not too high, because if the temperature is too high, you produce so-called residual thermal stresses, which are bad for the final structure. So even inside sigma S, you have a maximal temperature, which is not the same. Okay, so Tm, the maximal temperature, takes two values. It should be less than T phi outside sigma S, and it should be something like, some larger value than T phi in sigma. So anywhere you have a maximal temperature, but it's not the same. So you have a second constraint. So T must be between a lower bound and an upper bound. Okay, so that's my constraint. And I want to minimize this. Okay, good. So I do a gradient algorithm. I compute a derivative with respect to the position of this, and here are some results. So the domain sigma is a square, and sigma S is a smaller square delimited by the black line. So here is one initialization. You see the path clearly. The colors correspond to the temperature. Red is very hot, blue is very cold. and you see that the initial pass is, it should be, what is blue means that it is not melted. What is green or yellow is melted. You see that you have not melted what you wanted here on the boundary of your small square, but after some optimization, that's what you get. And actually, we were very happy to find this because this is a pass, a pattern of a pass which is known to be really very good for this kind of structure to build. So actually, by optimization, we recover something which was known by intuition, if you want. Here is a different initialization, and you see that you get some very complex pass in the end. So actually, if you vary the initialization, you find many optimal paths. Okay, so it's a problem where you have a lot of freedom and a lot of optimal paths. Okay, I don't remember which one. What actually, more or less, they all have more or less the same length in the end, because you need to melt this, and the amount of energy that you bring to melt is proportional to the length of the path. So they more or less have the same length. Okay, but there are many optimal paths. So now a different one. So now again. Sigma is a square, but you see that my structure is a cantilever. You know that the boundary of the structure is here. You have one hole here. That's an initialization. And after optimization, what you get is this very strange path, but it's doing the job. You see it is melted everywhere and not outside. Okay. You see that this one is not very good. Okay, so here this is another cantilever with 3 holes, and you see that the initialization was on purpose made stupid so that it's inside the hole. It's not a very good initialization, right? And it has some difficulty to find a correct path. In particular, you see that this tiny branch is not melted because the path is not going through this branch. So when you have a stupid initialization, you may have some difficulty to go in some bars in your structure and to melt it. So we choose a kind of not very clever initialization, and starting from a not very clever initialization, you have local minima, and you cannot go to something which is doing the job. Okay, now let me go to the final thing that I want to tell you, which is couple optimization of the shape on the laser path, right? So I have a shape. From now on, this was called sigma s before, I call it omega again. I have a path gamma, and so I want to optimize the shape so to minimize compliance. So I have a problem of linearized elasticity. I want to minimize compliance, but I want also to optimize the path gamma to minimize the length of the path and to be sure that I can build the shape. Okay, and so remember, the shape appears in the thermal constraint because I want the temperature to be above the fusion temperature inside omega, and I want it to be below outside omega. So I have a couple problem. Okay, I minimize, let's say, the compliance plus some Lagrange multiplier times the length of the path. I have 2 variable optimizations, the shape omega and the length of the path. I have 3 constraints, the volume of the shape, the fact that I'm sure that I melt omega with my path gamma, and that I'm not melting the outside of omega with my path gamma. And I recall the expression of those 2 constraints here. And so I have 2 state equations, one for the mechanics, for the linearized elasticity, one for the thermal equation, and I have 2 variables of optimization. It's a couple optimization. So how do I do that? Again, a gradient method. I do 1 step optimize omega, 1 step optimize gamma, and I iterate. Good, so I'm doing a cantilever, but for numerical purposes. I want to minimize the amount of CPU time. So I'm doing all computation on half the domain by symmetry. So my rectangle here, I cut it horizontally, and I'm just showing you the result on 1/2. You have to symmetrize it to guess what it is. So here is the initial structure and the initial path. So of course, the initial structure is very bad. The initial path is very bad. And that's what you get with the couple optimization. In the end, you see, you have to make this. I was a bit lazy. I did not symmetrize the picture for you. You have to imagine when you symmetrize it, it looks like a classical cantilever, except that the boundary of the cantilever is not smooth because it is adapted to the path. Okay, so in particular, you see that the thickness, is adapted to the path. So there is an influence of the thermal constraint on the structure, on the shape of the structure, right? Here, I do it for a different material. So that's the same initialization, the same geometry, but the material property are different. I don't remember exactly, but I guess that this one is less diffusive or something like this. Okay, I don't remember, but you see that if you change the parameters, not of the structure, but of the thermal diffusivity and thermal conductivity, you get something different, right? Okay, now that's another result for the same kind of a cantilever. So here I show you on the top right, the optimal shape if you don't take into account the path, right? And then on the bottom line, I show you two optimal results. The one on the left is I start from the initialization top left, and I do the couple optimization of path and shape, and I get something. The one on the right is I start from the optimal shape, I optimize the path only. So you see, on the right here, I first optimize the shape and then I optimize the path. On the left, I optimize them simultaneously starting from my crazy initialization. Good. Well, it's a bit different, but basically, that's the same. And what was also very interesting for my colleague, Christophe Tournier, is that he recognized patterns, which are classical patterns. You know, when you have something which is, you know, kind of a bar, you have some kind of a pattern of some zigzag pattern here so that you can really melt it. But it was not imposed by the user, it was found by the optimization. So probably it's better than something which was found by a user without any optimization. Good. I'm going to stop here just to tell you that there are many other problems here. In particular, I've been working a lot on the optimization of support, but I'm not going to tell you anything. And what is really fun is that I'm building such a kind of, well, I'm not personally doing it, but I'm working with colleagues who are building such a structure. So here you see a very small sample of a so-called MBB beam, which has been built, and then they are tested it, you know, saying that are optimal design, which are built, you know, using models which are very simplified in some sense. Are they optimal when you do the real experiment? That's still an issue. Thank you very much for your attention.
Thank you very